Okay, so as we said, we're going to continue talking about functions pretty much for the rest of the semester. There are some other topics we'll talk about, but we're now going to move ourselves into special classes of functions. So we're going to spend the next several videos talking about polynomial functions, but in these first couple of videos we're going to talk about specific kinds of polynomial functions, which are quadratic. But before we get into that, let's go ahead and do a definition of a polynomial function. So definition of a polynomial function. So let n be a non-negative integer and let a sub n minus 1 dot 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 a1 comma a0 be real numbers with an not being 0. And again, the reason we don't want an to not be 0, an is going to be our first term, and so we don't want that to be 0. So then the function f at x equals an x to the n plus a sub n minus 1 x to the n minus 1 plus we continue on the same pattern a2x squared plus a1x plus a0 is a polynomial function with degree n. Now, some examples of this, we've seen these before. F at x equals, x squared minus 3x plus 2. That's a polynomial function. F at x equals x cubed minus x plus 1. Polynomial. Basically, you have to have integer exponents. But then we also have, for instance, f at x equals 3, which some people don't think of. That is technically a polynomial function, because n is a non-negative integer, so it could be 0. X to the 0 power is just 1. And so these are all examples of polynomial functions. Things that aren't polynomial functions would be like g at x equals the square root of x squared plus 2x plus 1, because there's a square root there. Even though we have that x squared plus 2x plus 1 looks like a polynomial, the square root makes it not a polynomial. Or if we have g at x is equal to x squared plus 1 divided by 3x plus 1. This looks like we have polynomial functions there, but it's dividing them, so that's not a polynomial. It's actually another class of functions which we'll study after polynomials. So those are some examples of what is and isn't a polynomial function. Alright, so as I said, we're going to first focus on quadratic functions. Now, again, this is something we've really talked about before, so we're just introducing some new terminology and some other additional properties about quadratic functions. So the definition of a quadratic function is let a, b, and c be real numbers with a not equal to 0, then the function ax squared plus bx plus c is called a quadratic function. Now, this shouldn't really be too surprising. We've had quadratic equations. I suppose I should write f of x equals. As I said, this really shouldn't be surprising to us. We've dealt with quadratic equations, we've done the quadratic formula, so now all we're doing is now we're writing down an actual function that's called quadratic, and it's in the form ax squared plus bx plus c. Now, there is some things about quadratic functions that we want to talk about, so I'm just going to not even put up a great sketch. I'm just going to sketch in a y and an x-axis here, and then I'm going to just sketch a quadratic function here somewhere. So just some kind of parabola, and then I'm going to label that bottom point here, and then I'm also going to draw this here. And so we have some special names for this here. This point right here is called the vertex, and all quadratic equations have vertices. They have one. It's either a minimum or a maximum. It depends on what the quadratic function looks like. And then this dotted line here is called the axis of symmetry. And why we call it the axis of symmetry is if I rotate around that vertical axis, the graph lines up again on itself. So it's symmetric about that dotted line. Now, if we have here, again, my general form here, f of x is equal to ax squared plus bx plus c. What we do know here is we do know that a is greater than 0. How do we know this? This means the parabola opens up. So it opens up like that. And you can actually just go ahead and know that and just kind of think of that as transformations, why that would be the case. Now, if we have another graph here, and again, I'll just kind of be sloppy a little bit in my sketching here. We still have my vertex, and we still have an axis of symmetry. And we do still have our equation here, ax squared plus bx plus c, but in this case we know that a is less than 0, and the parabola in this case opens down. Now, how do I know these two things here? Well, one, it's the way it is, number one, but it's not just because I say so. If we think back to our transformations, if you had a negative, a being less than 0, that negative is not associated with our base function of x squared. You might say that's not the base function, you got x squared plus bx. We could transform it into a base function, which we'll do in a second here, and look at the transformations that are going on, and the base function would be x squared. And then, well, if there's a negative out in front of that, that's a reflection across the x-axis, so that would mean that it would be going down. So it really just comes from the transformations. It's not just, oh, a is greater than 0, it opens up, and a less than 0, it opens down. I mean, it is, but it's because of our transformations we've talked about the reflections. And then we also, have, if depending on the value of a, we also will still have vertical stretches and vertical shrinking as well. So we have all of those transformations still going on here with these quadratic equations or functions. Okay, so we're going to move on to, though, the standard form of a quadratic equation. I keep saying equation, I mean to say function. So the standard form is f at x is equal to a times x minus h quantity squared plus k, and here a is still not equal to 0. But this here, what has two important things here. The vertex is actually something we can take out. The vertex is a point, and when we have it here, this is the point hk. And if you think about it, that should make sense, because what do we have here? X minus h is a horizontal transformation, and then k is a vertical transformation, and we know that the vertex for just x squared is 0, 0, and so you're going to be translating it h units to the right and then k units up, so the vertex moves to hk. And then we also have that the axis of symmetry is x equals h, and then a, the sign of a, tells us if it opens up or down. And so, again, if we kind of look at this here, let's look at an example here. Find the standard form of f at x equals x squared plus 6x plus 7. Well, to find the standard form should have looked somewhat familiar. We're going to do what's called, again, completing the square. Now there is another way to get the standard form, which we'll talk about in the next video. So if we complete the square here, we're going to look at, well, b over 2 quantity squared, which would be 3, because it's 6 over 2 squared, which is 9. Now the only difference is because I'm not solving this, I'm going to still leave this as f at x equals x squared plus 6x plus 9. Okay, but I can't change anything. Well, this is what's kind of a little sneaky here. If I add 9, I'm just going to then subtract 9 and then add 7. And if I subtract 9, I haven't changed anything. But then what I'm going to do here is group these terms here together, x squared plus 6x plus 9, because I've completed the square, and that's going to factor for us. And so this factors to x plus 3 quantity squared, and then minus 9 plus 7 is minus 2. And so this would be my standard form, and what we have here is the vertex. Now you have to be careful here. The vertex is not 3, negative 2. The vertex is actually negative 3, negative 2. Axis of symmetry is x equals negative 3. And then, well, a is 1 here, and it's positive, so it opens up. And actually, just think of all the transformations we did. This here is transformation. The base function is x squared, parent function. It's a horizontal shift left 3, down 2. So the vertex, which is normally at 0, 0, gets shifted left 3 and then down 2. Alright, so let's look at another, and then of course we could sketch this, but let's look at another example that are a little bit more challenging. um, at least this first way of completing the square. As I said, in the next video we'll see another way. Let's look at f of x. Oh, you know me, I need to have black to start these problems. F of x is equal to 3x squared minus 6x plus 4. Now remember, to complete the square we want to have the x term being 1. The x squared term being a 1 in front of there. So this is what's going to look a little weird when we do this. I'm going to factor out a 3 and then have this as x squared minus 2x, but I'm only factoring it out of the first two terms, and then I'm going to have plus 4. Okay, now I'm going to just look at what's inside here and do complete the square. So what do I have? Well, I'm going to do b over 2 squared, which would be negative 2 over 1 squared, which is equal to 1. So I'm going to need to add 1 here. So f of x is equal to 3 times x squared minus 2x. Now I'm going to add 1, but I have to subtract 1 right away, and then you put your parenthesis in, plus 4. Now, this x squared minus 2x plus 1 factors, so I'm going to partially distribute this. And what do I mean by partially distribute? I'm going to do the 3 times negative 1, because then that would distribute that portion out, and I'd be left with f of x equals 3 times x squared minus 2x plus 1 minus 3 plus 4. And then this does, now we can finish and put this in the standard form. And this would be x minus 1 quantity squared minus 3 plus 1 would be plus 1. And so then we have a vertex of 1, 1. So axis of symmetry is x equals 1. And again, if you think about the graph, we'll look at graphs maybe in the next video, but the graph would be pretty straightforward. Remember, you can even think just transformations here. Base function x squared, then you have this shift to the right, you've got a vertical stretch here, and then you've also got a horizontal shift, up 1. Alright, so we can go on with that, but before we wind up this video here, we're going to do some, I think they're pretty straightforward examples of finding equations given information. So an example here. We'll just do one example here to wrap this video up, because these are pretty straightforward. Write the standard equation of a parabola whose vertex is negative 4, 11, and passes through the point negative 6, 15. Alright. So the standard form, remember, is f of x equals a times x minus h, quantity squared, plus k. Now, the nice thing is that they've given me the vertex, so I know that h and k are just negative 4 and 11. So let's go ahead and substitute those in right now. So f of x is equal to a times x minus negative 4, quantity squared, plus 11. Now let's go ahead and simplify a tiny bit. F of x is equal to a times x plus 4, quantity squared, plus 11. Alright, so I'm almost done it looks like, and I am kind of almost done. There's not a lot left to do, but I do have to figure out what the value of a is. How do I figure out the value of a? Well, I simply first take the point that I already have here, and I just substitute it in, and figure out what a is. And what do I mean? Well, I know it goes through negative 6, 15, so my y value is 15, and this is equal to a times negative 6 plus 4 quantity squared plus 11. Okay, then we're just going to solve this. So I'll just go ahead and subtract 11 from both sides. So we have 4 is equal to a times negative 2 quantity squared. So you'd have 4 is equal to 4a. And then you'd have that a is equal to 1. So f of x, we just write our answer down. Now it's 1, so I wouldn't write anything out there. X plus 4 quantity squared plus 11. Now just to maybe emphasize here, we don't typically write it, but I'll put it in here. We have 1 times. Because if you got something else for a, you'd, instead of having 1 there, you would have whatever value you got for a. Alright, so the next video here, we're going to talk about finding maximums and minimums of these, and then look at a couple of the graphs.